Hello there, it's Jason Gorman from Codemanship with a video about modular design principles for Python programmers. So in a previous video, we looked at the principles of simple design. Just a quick recap of those. First of all, we need to make sure that our code works and that it stays working, so we're always testing our code. Then we need to make sure that our code is easy to understand. As Ken Beck puts it, we need to make sure the code clearly communicates its intent. That is, you can understand what the code is doing by reading the code. So we look for opportunities to introduce names that explain what's going on. Then we look for duplication in our code and we remove that, but only if it doesn't make the code harder to understand. And then finally, from which it gets its name, we try to do it in the simplest way possible. As Kent puts it, use the fewest parts, if you like. We talked about how developers often find that a little difficult. Sometimes doing the simplest thing is a little harder than doing something complicated. And that's all great stuff. You'd be surprised how sophisticated designs can emerge as we apply those principles over and over again with each new test that we add. Particularly when we're removing duplication, because the opposite of duplication is reuse. And that's a great way of discovering those kind of reusable abstractions that we introduce into our code. A very objective way of doing it. So we're discovering the need for them rather than planning to have them. So all good stuff. And to be quite frank, if most developers observe the principles of simple design, most code out there would be a lot more maintainable. But it is possible to write code that ticks all of those boxes, but still has problems when it comes to changing the code, the cost of changing the code. And that's what we're going to be talking about in this video, the principles of modular design. So we think in terms of modules. So if we think about Python, we might be talking, for example, about modules in terms of Python files. But I'm going to be talking about modules today, both in terms of files, but also in terms of classes. So we're going to be thinking object-oriented. We're going to put our OO hats on today. And the first principle of modular design is about how much each module should do. And ideally, each module should only perform one job or only have one reason to change. So we're going to see an example in a minute of some very simple code that ticks all the boxes of simple design. But there's a bit of a problem in terms of we have a module that's doing two distinct pieces of work. And if we wanted to change how one piece of work was done independently of the rest, we can't because it's all in the same module. The other reason why it's important that modules only do one job is because, well, I'm going to use the analogy of modular hi-fis. So if you're familiar with the concept of a modular hi-fi, you've got your integrated hi-fis, where it's all one box basically, and combined in that box you might have a CD player and a radio and an amplifier and speakers. And then you have your modular hi-fis where you have one box that does each of those jobs essentially. You've got a turntable or a tape cassette deck or a CD player or so on and so forth. Now with an integrated hi-fi we get one choice. So I've got a lovely little JVC integrated hi-fi that I've had for more than 20 years now. And you get it works fine, but you get the JVC CD player with the JVC mini disc player, that's how old it is, and with the JVC radio, with the JVC amplifier and the JVC speakers, and that's your only choice really. With a modular hi-fi, you can have a Sony turntable with a Yamaha CD player and a Denon amplifier and whatever speakers you want. You've got so many choices as how you can combine those different modules into a hi-fi system. And we call that composability. When each of these modules only does one job, we get more choices about how the modules can be composed to do new things. So for those two reasons, one, because we might want to change one piece of code without necessarily breaking the rest of it. So when we split it up into separate modules, it's much easier to separate those concerns and change one thing in one place. But also, and we get much greater composability of systems when each of our modules is only doing one job. The next thing we need to think about when it comes to modules is how much they know about each other. And the general rule here is the less they know about each other, the better. So again, we go back to our modular hi-fi. We can plug the modules together very easily because they all have very simple interfaces. If I had to take the casing off my turntable and literally solder wires, so I'm exposing all the internal workings, the internal electronics of my turntable in order to connect it to an amplifier, well, that's not going to be very simple or cheap or low risk change. And it's a similar kind of thing with modules in software. When they expose how they do their jobs, particularly what data they're using to do their jobs to their clients, then when we change how that works, we end up having to change the clients as well. So the less the clients know about the modules they use, the better. Now, there's a style of design here, usually referred to as tell, don't ask, and we're going to see an example of that when we talk about a code smell called feature envy. But the general sort of rule of thumb here is that modules should tell each other to do things rather than asking each other for that module's internal data in order to do it themselves. So tell, don't ask, and we'll see a practical example of that in a minute. So they should do one job, they should know as little as possible about each other, so they should hide their internal workings, particularly hide their internal data. And the last sort of piece of the jigsaw for Python programmers, the last thing you need to know about, is when modules use each other's services, that should be done in such a way that it's easy to replace that supplier module with a different implementation without having to rewrite the client. In practical teams, that means that the client must not know what implementation of supplier they're using. So they should bind to abstractions, not to concrete implementations. So what I say here is that the dependencies for our clients should be easily swappable, usually using a mechanism called dependency injection. So the collaborators that they work with, the objects that they tell to do stuff, or the modules they tell to do stuff, are handed to them from the outside. They're injected in it either in a constructor or as a method parameter, or if you're doing functional programming as a functional parameter, so that the client decides, I want you to use this implementation, and the supplier doesn't need to know what implementation they're using. So there's think of it as a sort of a tripod on which good modular design stands. The first leg of the tripod is that each of those modules should only do one job. The second leg of the tripod is that modules should know as little about each other as possible. They should hide their internal workings. And the style of design is called tell, don't ask. And finally, modules' dependencies should be swappable, usually by dependency injection. So modules are composed from the outside by passing their collaborators in, so that the module doesn't need to change if we swap it with a different implementation. And that is particularly of interest when we're talking about stubbing and mocking using test doubles. So there's a big relationship between modularity and unit testability, how easy it is to swap external dependencies like databases and file systems with stub versions or with mock versions. But it's good architecture generally. It gives us a lot more flexibility in our design. We can replace one thing with another without having to rewrite tons and tons of client code. And we'll see how that works in our little example as well. Okay, now, because you're working in Python, you don't need to know about the fourth sort of leg of modular design because it doesn't really matter that much. But as we'll see, there is something related to that we do need to think about. If you're working in a statically typed language that enforces what we call binary compatibility, that is to say that if you're working in Java or C++, for example, if you write a class that uses another class, essentially that binding is done in such a way that if we were to change anything on the interface of that supplier class, even if that client isn't using it, the client needs to be recompiled, retested, and redeployed. And that, of course, can create problems. So we need to make sure that our interfaces are client-specific. That if you've got a C++ class and one client is using 3 of its methods but not using the rest, then we would extract a method specifically for that client so that it's only binding to an interface that includes the features that it's using. Now, that's the important phrase there, only the features that it's using. Now, in Python, as we'll see, there's kind of a flip side of that when we can end up sort of depending on things that we're not actually using. For example, unused imports. Unused imports create problems because if I decide to move that class to a different package, even though I'm not using it in this particular file, in this particular module, we can still end up in a situation where we break that module. So don't depend on stuff you're not using is kind of the flip side of presenting client-specific interfaces. The goal is the same. And it's very, very closely related to modules knowing as little about the rest of the system as possible. Okay, so those are the principles of modular design. We're going to do a little demonstration now. So I've got some example code here. And this is a very simple piece of code that calculates quotes for carpets, fitted carpets. To calculate a quote, we need to know the length and the width of the room that the carpet is going to go into. We need to know what our price per square meter is for that carpet and what the pricing policy is, whether we want to round up to the nearest square meter. So if it's 10.5 square meters of carpet, we would charge for 11 when we fit it, or whether we don't. So that's like a simple true or false. And I've got a couple of tests here. So we're going to start ticking off the boxes of simple design before we do anything else. Let's first of all run our tests. Oops, that's the wrong. Let's run our tests. So I've got a little test module there, and inside that we'll just run the single. I won't bother using unit test to run this. Run our single unit test, carpet quote test, carpet quote test, and hopefully we'll get 2 passing tests. Lovely, 2 passing tests. So we've got 1 test where we're not rounding up and another test for when we are rounding up. So let's take a look now inside carpet quote. That's the first box of simple design ticked. It works. The second box is it easy to understand? Does it clearly communicate its intent? Well, I've asked people and they say, yeah, they can understand what's going on here. We calculate the area of the room. We round it up if we need to, and then we multiply the area of the room by the price per square meter of that area, whether it's been rounded up or not. So it's all pretty straightforward. So we've ticked the second box. The code clearly communicates its intent. I can't really see any duplication here. There's a little bit of duplication in our tests, but if you go back to a video I recorded on duplication and the rule of 3, there's only 2 examples of the duplication here, so I'm not too worried about that. I'm going to leave that in for readability. And finally, is this really the simplest thing I could have done? Well, I suppose I could have made it a pure function. But really, I think, honestly, there's one class, one method, and a constructor. I'm happy with this. I think it's pretty straightforward. I would struggle to make it much simpler than this. Okay, so we're ticking all the boxes of simple design, but there is a problem. Our client has informed us that sometimes the area of a room is not the length times the width. Sometimes the room is not a rectangle. Sometimes, for example, the room, believe it or not, can be circular or it can be L-shaped. So they say we need the ability to have different shapes of room. So what we're saying here is we can imagine wanting to change this code here, but not wanting to change the rest of it. And that's kind of the rule of thumb here. When I look at a module, I'm thinking, based on my understanding of the requirements, would we need to change this? Can I see us needing to change this or to vary this at runtime without changing this? And the answer here is yes. We've been explicitly informed of that. So what we need to do now is we need to split this module up essentially so that we have each module only doing one specific job. One to calculate the area of the room, however that's done, and another to calculate the price of the fitted carpet in that room. And we want those modules to hide their internal workings. So for example, if we want to calculate the area using length and width, or using, for example, the radius of a circular room, those pieces of information and how that calculation is done need to be hidden inside whichever module is doing that job. So we need to achieve encapsulation. And then we also need to make it so that we can swap a rectangular room with a circular room, or a circular room with a triangular room, maybe even, without having to rewrite any of this, oopsie-daisy, any of this code. I'll just quickly rerun my tests now that I've done that. Oops. Okay, so we're going to try and tick all of the boxes of modular design. So we're going to refactor this code so that we've got modules that each do one job. We've got modules that hide their internal workings. In particular, they don't expose their data, they encapsulate that. That's the word we're looking for. And finally, we want to make it so that the dependencies are swappable. So if one module is using another module, it doesn't know the implementation of the module that it's using. So let's do this refactoring. First of all, we're going to need some new objects here, some new classes. And an easy way to do that in Java or C# would be to use a refactoring called introduce parameter object. I think in Rider for C# it's called transform parameters. And what that does, it takes parameters of a method or a constructor and turns it into an object with fields, and those fields are set in that object's constructor, and then that object is passed in as a parameter. Now, lucky us, PyCharm does not support introduce parameter automatically, so we're going to do this manually, and we're going to do it in stages. Stage number 1 is to imagine the class that we want to create as this parameter. So this is going to be a room, and it's going to have a length and a width, basically. So let's just, step number 1, let's imagine there's such thing as a room. And what I want to do is I want room to be passed in as a parameter of this. Now I can actually use an automated refactoring here just to make things a little easier. So let's add a parameter for room. Let's call it room. And what we're going to do is we say, look, create an anonymous instance of that and pass it in from the test code so that it's not null. Okay. Now I'm going to do this now. I'm going to hark forwards, bit of foreshadowing here, to a video I'll be recording about changing legacy code. And there are people who will tell you that if you're changing legacy code but you're using automated refactorings, then you don't need to retest the code because automated refactorings are guaranteed not to break it. Well, let me demonstrate what happens when you fall for that snake oil. Okay, so let's perform this automated refactoring. And what the tool will do automatically there is it will introduce that parameter, but lo and behold, my code is broken. And the reason it's broken is because it didn't add an import for that new class. Naughty PyCharm. So I have to fix it there. So there, just to disprove the theory that if you use automated refactorings, it's guaranteed not to break your code. That is not the case. Okay, let's rerun our tests. So we're kind of in the early stages of doing this introduce parameter object refactoring. That's my goal. Okay, now what we're going to do is we're going to assign this to a field since it's there. We can do that automatically. And we can, because it's cheap, retest that. Okay, now that we've done that, we're going to add data. So let's create a constructor for this. This is how our parameter object is going to work. And I'm going to add these two fields. I won't delete them from here. I'll just copy them. Okay, and I'm going to assign them to fields. And that's going to create our data object here. And to complete this refactoring, what I'm going to do is I'm going to pass the data in the right order. That's why I did the copy thing, just to make sure that they are. And I think they're both identical in both tests, so let's just reuse that. And that's the complete refactoring there. So we now are passing in this parameter object that has a length and a width that are set in a constructor. So that's introduce parameter object. Let's rerun our test at the command line there. Lovely. So far, so good. So we now have a room and it has a length and a width. And we could use the room in our method here, but I'm not going to. What I'm going to do instead is I'm going to introduce a new method. So let's extract. I can do this one automatically. Let's extract a new method. Let's call it calculate. We're going to just room area. There we go. Room area. And immediately retest. That's good. Keep it working. Always be testing. Now here's the thing. Now that I look at room area, so I mentioned this code smell in my introduction when we were looking at that slide. It's called feature envy. And it's when an object of one class has envy for, is using many features of another class, giving a strong indication that method is the wrong place. Now these now really should be features of room. I can actually make it totally explicit here, just to make it clear. Let's rerun our test. Okay, so that's called feature envy. The room area is not about the carpet code, it's all about the room. It's all about room. So this method is in the wrong place. Now I'm just going to undo that and you'll see why in a minute. And when you undo, don't forget to retest. Whenever you think it should work, see that it does. What I'm going to do is I'm going to move this instance method from carpet quote to room. Now, again, if we were working in C# or working in Java, we would have an automated refactoring to move this method. It would do it all for us. But we don't, because we're working in a dynamically typed language, so it doesn't have the type information necessary. Because essentially it doesn't know what type of object this is, or any of these things are, any of these fields are, so we don't have an instance to move it to. So what I'm going to do instead is I'm going to do this manually. And the way to do move method manually, the simple way, is to cut the method. And then what we're going to do is replace that method to a call to room area on room. So let's imagine that exists. And then we paste it onto the room class like so. So we've moved it there. And then that's move method, move instance method. There you go. So now room is doing its job. Room.room area sounds a bit weird. Let's clean that up. So I'm just going to rename this to just area. Okay, let's do it. And retest. So I'm getting a little bit of support here from PyCharm in terms of refactoring, but it would be great if I had refactorings like introduce parameter object and move method, because that would have made this so much quicker. Okay, but at least the way we're doing it is safe. We're taking baby steps. So if you watched our video on Python refactoring, it's important to take baby steps. Okay, especially if you're doing it manually. So that's room. We're telling room to tell us the area now. So we tell, don't ask, and that feature env is gone, which means let's just make it a little more explicit here. If I rename these to follow the convention of using underscores to denote private, so length and width essentially are supposed to be private. No one else is supposed to know that it has these fields or how it's doing its calculations. So we're encapsulating, we're hiding the internal workings of room. Let's retest. Lovely. And now we're going to do the same thing with the code that calculates the price. That's this code. So it's using the area. What we're going to do is we want to extract this code into its own method and move that method to a new class. Let's call it carpet. But before we do that, we need a class to move it to. So we're going to introduce another parameter object. First of all, actually, let's just declare that parameter object. Class carpet. Let's imagine it exists. Okay, now let's pass that in. So we're going to change the signature of this method again and add a carpet parameter. And this refactoring, as we know, will break our test code. So let's fix that. Consider this a bug report, JetBrains. There we go, lovely. And now what we want to do is we want to add a constructor to that so that we can actually pass in the data that it needs. When it comes to deciding what data objects require, I'm very much in the habit of giving the data it needs to do its job. So I sometimes like to see a function or a method first that's doing the job, and then consider, okay, well, what data will be required to do that job then? So as far as I'm concerned, objects exist to do work. They're not carriers of data. That's not their job. Okay, now we need a price per square meter. In actual fact, let's just be methodical about this. Let's cut these and paste them in so they're the right names and in the right order. Let's assign these to fields. Nice, quick and easy. Okay, and now what we need to do is we need to pass in the data that object requires. So at the moment it's just a data object, it just holds data. This time it's different. So we are rounding up in this second test. Okay, and let's retest. Lovely. And similar kind of thing here. We now need to isolate the code that is doing the work that we think carpet should be doing. So let's extract a method, and that's the price of the carpet. And then we're going to move this method to where it really belongs. It's really not about the carpet code, it's about the carpet. So let's cut that. Let's replace it with a call to carpet, and we will need to assign that to a field. Should have remembered to do that. Okay. And then let's paste in the method that we're moving and rerun our tests. And we're all good. Bit of cleaning up to do here. We don't need these other parameters anymore. We just need the room and the carpet. So let's change the signature of this, and basically let's get rid of the length, the width, the price per square meter, and whether or not we need to round up. So we're simplifying our constructor, which means we can't set those fields. Look how simple carpet quote is now. Almost doing nothing. All it's doing is combining those two calls. And we could probably inline this. So it's just a single line there. Since we've got a method called area, do we really need a variable called area as well to explain what that method is doing? Okay. And finally, because we don't need to expose these anymore, let's denote the fact that they are private. An underscore. There we go. So this is hidden information, forbidden knowledge that other classes do not need to know. Okay. And then finally, let's just make it official. Let's move these to their own modules. Okay. And just make sure I haven't broken any imports there. And similarly here, this is just carpet. Okay, bit of GitHub going stuff going on. So now when we take a look at carpet quote, first thing you will notice is it has no imports because it needs no imports, because these objects are being passed in. It doesn't need to know what the implementations are. Remember when I talked about modules should not depend on things they're not using. It doesn't need to know which classes of room or carpet it's using. They're being passed in by dependency injection. And this opens up some real distinct possibilities here. If we take a look at our test code, let's just make it official. Let's imagine there really is such a thing as a circular room. Let's call it a round room. And we're going to give it, well, we can be explicit here if we wish, but we don't need to be, of course. Let's not be. Let's just make it another object. And of course, if we wanted to make it type safe, etc., in the real world, we might want to use some kind of abstract class, import that library and do that. But I'm not going to do that. What I'm going to do instead is I'm just going to do a bit of duck typing here. So let's imagine our round room has a radius. Let's make that a field. And I'm actually going to make that private. There we go. And let's imagine we have our area method, which has no parameters, so the client doesn't need to know how it's done. And we're just going to return, well, people don't make circular, well, they suppose they do make circular carpets, but let's imagine that we don't make circular carpets. So in order to buy a round carpet, you have to buy a square carpet that fits that radius. So it would just be the radius squared, basically. Would be the area of carpet that we would require. And of course, we're working in Python, so I'll need to add self. A nice bit of language redundancy there. Thank you very much, designers of Python. And And what I'm going to do is I'm going to substitute a room here with a circular room. So if we said this was a round room with a radius of 10, for example, then we would expect the price of that fitted carpet to be 10 squared times the price of the carpet, which is 10, which is £1,000. There we go. So I've not changed carpet quote at all. Not changed carpet quote at all, but I'm introducing a new kind of room. Let's see if that actually works. Look at that. Oh, no. That's why. This is why we test. Silly Jason. There we go. Okay. Let's try again. And there we go. So I was able to introduce a new implementation of room, and that might not just be a round room or an L-shaped room. It could be a stub room, for example. So if we just want to test the logic of the carpet quote, we can just introduce a stub room that returns a hard-coded area just to check that part of the logic is correct. But it allows us to change our architecture in very simple ways, but very powerful ways. For example, replacing a rectangular room with a circular room without having to rewrite all of the client code. So this is a simple design, but also a much more modular design. It is naturally less simple than the non-modular design. And this is what a lot of developers complain about. They go, well, now you've introduced lots of new classes. But we're having to strike a balance here between achieving the flexibility that we can get when we need modularity, that's composability in particular, and the ability to change one part of the system without changing the rest. We get that advantage, plus other advantages of modularity. We can now have systems tend to become much more manageable when they're broken down. Manageable, for example, for version control and for testing and for documenting and for understanding. But there is a price you pay for that. We have undoubtedly made it more complicated than it was. We've added complexity. And so you need to be very, very careful with modularity. And in particular, you need to be very careful about the names you choose for modules and the things that they do. Because modularity, in terms of the complexity it introduces, it can actually help us to simplify the way that we understand systems when we break it down into these little boxes, if nobody needs to look inside the boxes to understand what they're doing. So that takes us back to code that communicates its intent. Modules need to clearly communicate what they are and what they do so that we don't need to look inside of them. So we can just literally look at the code that uses that module at a higher level. And that allows us to construct, to compose systems at the highest level, look very, very simple, and essentially tell the story of what's happening without revealing how that work is being done. And that takes a lot of getting used to. And a lot of developers are not accustomed to reading highly modular or highly composed code. Because when people study computing, for example, they're often dealing with very small examples and they're dealing with very algorithmic examples where they're used to seeing all of the code in front of their own eyes. And then when you start breaking it down, there can be a bit of a barrier to understanding that, but also inexperience at choosing good names for modules, choosing names that reveal what these modules do. So there's a bit of a caveat with modularity that with less experienced teams, sometimes I encourage them to sacrifice some modularity. I'm still really, really hard on them about external dependencies. When it's something that they really, really need to stub or mock, for example, I'll say, no, that needs to be separate. But sometimes I'll dial it back a bit, dial the modularity back a bit to make the code more familiar to the team, because as important as modularity is, the ability to understand the code is still more important. So modularity, I would say, in terms of the hierarchy of needs, it comes after simple design. So there you go. That's modular design principles in Python. Similar principles apply if you're just doing straight functional programming. You've still got modules in the form of Python modules. You still need to be making it so that each of those modules is doing only one job, so that as little of that module is exposed to other modules as possible. So ideally, you want modules that are only exposing one or two functions, and everything else is private and internal. And when modules use other modules, you need to be looking for ways wherever possible, particularly when we're talking about external dependencies or separating concerns, such that functions can call other functions without necessarily knowing what implementation of function they're calling. And the way that you achieve that, again, is by dependency injection. You can pass functions in as parameters. We call these higher order functions, when a function that accepts functions as parameters or returns functions. And in terms of encapsulation, we can also do something very similar using closures. So we can have a function that uses data that's passed into an enclosing function, so that people can use that function without having to pass in those parameters, without having to know, for example, that our enclosing area function is using a length and a width rather than a radius, because it's the outer function that knows that gets that data. So you can do similar things with functional programming and you get the same kinds of benefits. So there you go, modular design, very, very important for writing fast running tests. And therefore, as we're going to see in later videos, very, very, very important for continuous delivery and for the pace of delivery, for maintaining the pace of delivery. So this is a kind of a crucial topic. So hopefully it's been of some use. I'm going to post a link to the before code so you can have a go at doing this refactoring yourself. Remember to be super disciplined and take baby steps and always be running those tests.